So there are 7 billion smartphones and 2 billion computers in use worldwide. People are playing video games more than ever before. Video gaming has become part of mainstream entertainment. During COVID-19, the number of gamers increased by 38%. After lockdowns ended, overall play time decreased from peak levels but remained higher than pre-COVID levels. The current video game market valuation is at least $250 billion. In 2030, it is expected that the market will grow by at least $350 billion. As AI automates repetitive tasks, people will have even more free time. Where will they spend it? Gaming. This will unlock more opportunities for the small gaming productions and 2D indie game developers. Video game development is a lot different from traditional software development. It requires a real-time performance, graphics rendering, and physics simulation. Most other softwares don't need to care about it. And unlike typical apps, games must be continuously run on complex systems at high frame rates while delivering an interactive experience. A video game is a blend of art and clever engineering, making it both technical and creative. Although a lot of technical work is handled by the engine under the hood, there are still development concepts you need to understand for game creation. Before we dive into those, you should know that there is a free PDF guide you can download from the link in the video description that covers 25 topics related to game development. Most guides explain concepts using engine-specific terms that are hard to grasp, but this PDF makes them much easier to understand. Let's begin. Watch this demonstration closely. Back in 2009, Mythbusters teamed up with NVIDIA to show how GPUs process graphics in parallel versus how CPUs work serially. They used paintball guns. One shooter represents a CPU core and dozens of shooters representing GPU cores to paint the Mona Lisa on a canvas. The parallel approach finished dramatically faster. This same principle is how video games load images and resources and turn them into an optimized interactive virtual environment in real time. Now that you understand how GPU renders everything so quickly, let's break down actual building blocks that make up a game. Scene graph. A scene graph is the parent node that holds everything together. Think of it as a family tree for all the objects in the game. A player character might be a parent node with child nodes for their weapon, health bar, and shadow. When you move the player, all the children move with them automatically. Scene graph makes managing complex objects easy and simple. Texture and assets. Assets are game resources like images, fonts, JSON data, etc. A texture is image data loaded into GPU memory. The Assets API manages this loading and caching. Proper asset management ensures resources are loaded efficiently. It prevents memory leaks and provides loading progress feedback. Sprites are the visual building blocks of the game. Every 2D image that is created from a texture is a sprite. Sprites give easy access to position, rotate, or scale the 2D images. Game loop or ticker. Think of ticker as the heartbeat of the game. It's what keeps the game alive and running code over and over again. It keeps the air flowing or the fire burning. Without the ticker taken, nothing will be moving. Collision detection. It's a widely used term for checking if two or more game objects are overlapping or touching. In games, if a bullet hits a character, it must be detected. Based on the object shape, collision detection algorithms vary, with common approaches including bounding box, circle, sphere, polygon, and pixel-perfect collision detection. Tweening. Tweening is a method to make the animation smooth. If a jump action has 10 different still images that makes it look like a jump, tweening makes it smoother for 60 FPS or more. Tweening is usually done by the libraries and game engines. Culling. Culling is the process of not rendering objects that are not visible. If an object is off-screen or behind the camera, they don't need to be rendered. Culling removes objects from outside of the view, saving hardware resources and giving a smooth gaming experience. Rendering. Rendering is how game draws everything you see on screen. On every frame, the game takes sprites, scenery, effects, and turns them into pixels on the display. It usually happens so fast that it creates the illusion of smooth, continuous motion, typically running at 30, 60, or even 120 plus frames per second, making the game world feel alive and responsive to your actions. Shaders. Shaders are programs that run on the GPU to control how graphics are rendered. They manipulate pixels and vertices to create visual effects impossible with standard rendering. Glowing edges, water reflections, distortion effects, color grading. Shaders make it happen. There are vertex shaders, which modify geometry, and fragment shaders, which modify pixels. Pick an engine, download the PDF guide from the description, and start building. Your first game won't be perfect, nobody's is, but every game you make teaches you something new. The hardest part isn't learning the concepts, it's actually starting. Now go and create something.